Fine, I got it. Wow, nice computerized voice. Fine, I'll start now.
1 second. Can you like switch off the record, like pause it or something?
Yeah, sure. Yeah. Uh, all right, guys. So, as I said before, we'll be going over the history of open source a little bit. I know history lessons are boring, but actually, this is pretty interesting. And it's also the history and what kind of open source or free software you're dealing with largely determines how you work and what path your project takes and what kind of people are allowed to work on it. So it's a bit important to know. So in short, in around 1985, this guy named Richard Stallman. Okay, so he came up with something called GNU, and GNU stood for is it's a recursive algorithm, a recursive acronym. It stands for GNU, not Unix. So basically, he wanted to build an operating system that was an alternative to Unix, but for free. So what happened was in USA, there's this college called Berkeley. It's pretty famous. So uh, they had their own version of Unix called BSD, Berkeley System Distribution, and this Unix port is extremely popular. In fact, Apple's Mac OS is the port of BSD, I believe. So this was really popular, but then Richard Stallman did not like how much control some bodies or some people had over BSD, so he started GNU. The original goal of this GNU project was to create an OS. So this OS was called GNU Herd and a set of tools. Okay, so like all of your GNU tool set. So this included a famous compiler called the GNU Collection, which we today call GCC. So all of these tools were developed for this GNU Herd OS. So now what happened was the GNU project started, and that's when free software. And he started a company, or rather an organization called the Free Software Foundation, a short for FSF. Now there are a few different words that you'll see on the internet. One word is freeware. Okay, you might have seen this word somewhere. Another word is free or libre software. Okay, and the third term is open source software. So, contrary to what most people believe, these are not the same things. They have different meanings. So, when you're dealing with freeware, so freeware basically means that the software is free to use. It doesn't say anything else about the software. Like, say, you get a free copy of WinZip with WinRAR or something, you download WinRAR and you use it to open a file or unzip a file. You don't know anything else about WinRAR. You can't access the source code of WinRAR. You can't modify WinRAR. The only thing you know about WinRAR is that it's free to use. So this kind of software comes under the freeware label. Okay, and free or libre software. This one is what the free
Android is
software.
not free. It's actually
Yeah,
paid.
yeah, it's actually paid, but okay, I think you get the point, right? Sort of. So, free or libre software. So, this is what the Free Software Foundation promotes. Okay. So, this is actually a little more restrictive than open source. It uses something called a viral license. Now, we'll come to that later. But for now, understand that free or libre software means that one is you are free to modify and read the source code, and you are free to distribute the modified product for free. Okay. And open source comes with the guarantee that you can download the code and view the code, but depending on the license, you might not be able to distribute it for, like, you might be able to earn money from its distribution. We'll come to that distinction a bit later. Now, so see, coming back to the history part, when GCC, I mean, when the GNU tool set was being developed, at that time, herd was not going anywhere. The idea of this GNU herd was to develop something called a microkernel. Okay, like we're talking about operating systems here, so it was an idea to develop a microkernel, like a very small kernel where which has controls only your main core OS features, and everything else is just plug-in. Like you have to plug in stuff to the kernel as modules, like everything from USB to interrupts to keyboards or whatever. So this kind of kernel is actually very hard to develop, and the committee took forever to actually finalize the final design. So by then, a young man named Linus Torvalds had come up with something called Linux, which was his own version based on Minix, which was based on Unix. So he created Linux, the Linux kernel, and initially he only created a kernel, right? So a kernel is not a complete operating system. What the Linux developers did was they took most of the GNU tools and integrated it into Linux. Like uh, like 50, 60, 70% of early internet was like 90% of it was GNU tools. Everything from the utility used to view stuff like the GUI manager, like GNOME, to the file system manager, to the stuff used in the command line. Everything was based on GNU. So, like till date, there's a dispute about how Linux should be called. Most of the GNU enthusiasts say that it should be called GNU/Linux, and the Linux people are just like, so what if it uses GNU stuff? It's its own thing, so we should just call it Linux. So again, the core of now coming back to the differences. Now the core of open source software is licensing. Like if you've gone through GitHub repos before, you'll often see a license file, right? Like well, let me just show it to you in case you haven't seen one. So like you can see on my repo here, which I put on screen sharing just now. This is my repo, and it contains a copy of the MIT license. So MIT license is just one of the many open source licenses out there. And these, like, you don't, like, all of this is inbuilt into GitHub. All you do is like create a new file and start typing license. You'll get a list of licenses that you can apply. So this license, it gives you permission to download my code and use it for commercial use. You can modify it, you can distribute it, or you can use it for yourself. On the permissions thing in the top, you can see that the limitations are it doesn't carry any liability or any warranty. Like if the code breaks or you use it somewhere where it's critical and it doesn't work, or it suddenly stops working, then I am not responsible for what happens. So this is like an example of an open source license. Okay, so now this is where the difference between free libre software and open source software becomes very obvious. According to the free libre license, for example, you have licenses like LGPL or lesser GPL and GPL v3, like all of these. It stands for GNU public license and lesser GNU public license. So these are your free license, free FSF licenses. Okay. So what these say is, you can take my code and like use it in your project, or you can build a project on top of my code, but you have to release your code also for free. So I so you're following me so far. Is anyone having any confusion till here? No, right?
भैया वो फ्री लिबरल वाला एक बार फिर से बताओ ना.
हाँ हाँ बता रहा हूँ. So yeah, so this thing Libre says that you are like free Libre license says that you can take my code, you can build on top of my code, you can modify my code, but if you are distributing my code, like if you are selling, if you are making your own stuff, then you have to distribute your code also for free under the same license. Okay. So basically, suppose you know Red Hat and Ubuntu, right? Like two popular Linux distributions. So what Red Hat does is, like they take the core Linux kernel and they build a product and they offer tech support. Red Hat is also a Linux-based OS, but the thing is, Red Hat costs money. Like you have to pay for it. Under a Libre license or FSF license, this is not allowed. Like you can't commercially profit, or you can't make a closed source copy. Like, okay, you can commercially profit, but you can't hide the source code. Like right now, it's possible that under an open source license, that I can take somebody's open source code, modify it or integrate it into my code, and then sell that code as proprietary software, like that others can't use. Like, I mean, others can't see the source code. They can only use the software. Like Windows is a proprietary software. So in free software, so a lot of people had problems with this. Okay. Now when this Libre licenses or free licenses came around, most companies or corporate companies considered it a disease, because they were like, okay, this is a big problem. Suppose I want to make a file system manager, like you have your Windows File Explorer or Linux File Explorer or XFS or some other file management system. Suppose I'm building an OS, like now it might seem strange, why would somebody build an OS? But remember 20, 30 years back, there were like 30, 40 different operating systems for different systems and different architectures. So suppose I'm building an operating system and I find that, okay, this guy developed a open source, like a free software product, and I can just take his code and put it in my OS and run it, and I'll have a working file system. But because of the things that LGPL and GPL say, now I have to release my entire operating system source code for free. So in a way, the license is like a virus. This is what is known as a viral license. Okay. So, and there is actually still a lot of free software out there that meets this strict definition of that you have to distribute it for free. So some things actually benefit from this kind of license, like say licenses applied to programming languages. Like suppose there's only one company which is developing a compiler for a programming language. You don't want that company to suddenly declare tomorrow that you have to pay to use the compiler. So if you put a license like this, you can ensure that your software is never going to be like used proprietarily. Wherever it's used, the code is going to be open source, or like it's going to be public. So this is the viral license. Now we come to our open source licenses. Okay. So our open source license examples are your MIT license, or your there are other ones. I think there's a Berkeley license, there's an Apache license, etc. So these licenses are open source licenses. So what happened was, sometime in the 1990s, they decided that, okay, this way nobody is ever going to make money from free software, or nobody is going to want to work in free software because of how restrictive the license is. So we're going to make something called open source, and they actually made a body called the Open Source uh, Foundation or something it's called. So what this license, MIT license, says that you can take my code, you can view it, you can modify it, you can distribute it for free, or you can include it as a part of something that's paid. Got it? So it's like it's looser than the LGPL or the viral license. So I hope this clears up the difference. So this is not a viral license, because if I open source some part of my code and you include it in your software, you don't have to open source your thing. like you can see an example now. Windows offers something called WSL, okay, Windows Subsystem for Linux. So it includes a whole copy of the Linux kernel in Windows, so that you can run Linux stuff alongside the Windows OS. Now, even though this Linux kernel is integrated into Windows OS, Microsoft doesn't have to release Windows source code for free. That's because Linux itself is under an open source license and not under a FSF license. So I hope that makes that difference clear. Is it everyone clear up to this point, or is there any doubt? So I'll take it that there's no questions, and I'll move forward. So this is your licensing stuff, okay? And this is very important because obviously, what kind of license your organization has, suppose when you come across an open source company or an organization, you need to know what their terms of work are, what they're promising to their users. And when you are developing an open source project, it's not really open source until you put a license on it, right? Because other than, till that point, it's just assumed that you're sharing your source code with somebody. And but once you put your license actually has legal repercussions if there are disputes regarding how your software should be used, or if somebody is attempting to make money off your stuff. So now we come to the example of the most successful open source software in history, which is GNU Linux or Linux. So this is a kernel, and it forms the base for many operating systems. If you're doing open source software development, you can work with Windows, but because the way the open source software world works, it's pretty much a given that unless you're developing for Windows, you will have to work with Linux. That's because there's a lot of very specific tools that you require to build and run your software. Like there's a difference, right? At one point, you're writing a program with one file or a few files, and then it goes to a full-scale app or a full-scale software which requires multiple programs and multiple building steps which have different parts. So for that, like suppose you might need make. So GNU make is there. So make is actually like a full-blown programming language in itself. And using make, you can specify exactly how your software should be built. That is, like, instead of like having a software where you need to tell 10 steps, like, okay, put this file in this folder, then run this command, then run this command, then run the third command, then run the fourth command, and finally your software will compile on your local machine. Inside your make file, you can specify all the steps, and first do this, then run this test, and then install the software. So then that just person just needs to find the make file in the software after they download it from GitHub or any other version control. Will come to that, and they can run the software in one step. So you will need make. So make is a GNU product, which is to say it was built for uh, like it was built originally as a part of the GNU project, and now it's a part of Linux, and it has been a part of Linux for 40 plus years. So just like make, if you want to build a product for separate operating systems, suppose you want to make something that runs on Mac OS, Windows, and Linux, then you use CMake. What CMake does is you give it a long set of instructions. If you detect this operating system, do this. If you detect this operating system, do this. Like suppose it depends, like you're building a C++ project. Now, if you're doing the project on, if you want the project to run on a Mac and on a PC and on Linux, then you will have to invoke a different compiler for each one. Because with Mac OS, the default C++ compiler is called Clang, or like Clang, which is what I use. Now, Linux can run both Clang and GCC. macOS runs Clang by default, so it'll look for Clang. Like your program should look for Clang if you are installing a C++ project. Now, if you are using Linux, GCC is the default. If you are using Windows, then Windows has its own flavor of GCC called MinGW or something. So CMake is again a GNU software. So just like this, right? As you're developing software, then you have your build system managers. Like when you're building your software, when you need to link all the files together and build it into one software, then you will need a tool to actually build the software. So then you have things like Ninja and LLD linker and Gold linker. So again, all of these are written for Linux, specifically for Linux. So if you have to do open source development, use a Linux distribution. Then again, if you're starting out with open source, then you need to know some things, some basics of Linux, without which you can't get off the ground. And here I'd like to again, yeah, like if anybody has any questions, please ask, because then again we'll move forward with even more keywords. Any questions? Okay, somebody said, Pratik says it's all clear. Fine, so let's move forward. So now, suppose you're starting with Linux, there's a few things, right? One thing is you have to get really comfortable with the terminal. So this terminal, and by extension, you have to get comfortable with Bash. Now, you have to realize one thing is that I've noticed this behavior even in like all of the guys who are learning software, like development in point blank, is you're not treating your programming languages or your frameworks or your IDEs as tools. You're treating them as things to be learned. And this approach is going to get really, really frustrating if you are setting out to actually develop open source software. Why? Because see, like there are books of 500 pages and courses that are 1 month long on Bash, courses on Make, courses on Ninja, and courses on Clang. And for every single open source software that you use, it's going to use some version of some software that you've never heard of. So if you try learning everything about it before you actually start the development, right, you're never going to get anywhere. So just like learn enough that you can get the job done and move forward. Later on, you can, as you work, you'll get to know the tool more deeply. Same goes for programming languages, right? I mean, yeah, you might favor Python over C++ over Java, but ultimately all of them are written in English. If you can read English and if you have at least some amount of programming aptitude, you're going to understand what different programming languages do. So get used to the trend of, like learning just what you need, and like starting off with that, and then, slowly building upon your knowledge as you build. So you're going to need the terminal. You need to know how package managers work. So, uh, uh, package managers are ways for you to install software. Earlier Linux, I mean Ubuntu used apt lot, advanced package toolkit. Now they prefer snap installs. There's also homebrew, which uses brew installs. Then there's pip for Python packages. So all of these are ways to install software, like uh, uh, from your terminal. Then again, these things are there. Then there's your permission commands. You have stuff like sudo, then chmod. Then you need to know how to deal with tarball files. You need to know the common command like cat, cd, and ls, and all that stuff. So the best way to do this is actually to download a Linux distribution and try to use it as your daily driver. Like try to use it as your everyday stuff. Like just try to use it as your everyday OS. You'll get stuck somewhere. You'll search for how to do it in Linux, and slowly you'll piece it together. So yeah, that's the case for Linux. Now we come to version control. Okay, so this is the heart and soul of open source software development, because you have to realize one thing is that in all proprietary software, a software that's developed in companies, all of the software is developed in an office where you have some manager and some committee that clearly lays out the goals and tells that this is what we have to do, this is when we have to do it, this is what we need, this is what we can remove. Open source doesn't work that way. I think it's clear by now, because all of the work is remote. The people rarely ever meet together, and again there's no legal force. Like, you don't have a job to lose, right, if you don't work in time. So this is where version control systems come in. Version control systems are responsible for maintaining different versions of your software, and you already know them. Like, you have Git, you have GitHub, which is used as a graphical interface. Then you have GitLab, you have Bitbucket. There are others too. So all of these are stuff places where your code is hosted. And now there's a lot of features integrated into GitHub itself, like automatic checks, and like stuff to identify which programming languages are used in which repository and all that. So you have to get familiar with Git and GitHub, because using Git you can not, like, even when you're not pushing stuff to like you're not pushing stuff online, you can still maintain a local copy. Like, say you wrote a app or an Android app, or or you made a website, or you made some piece of software that has 50, 60 files. You made one change, and that change somehow broke your whole thing, and it's no longer compiling or working. So using these tools, you can easily roll back to the last point where it was working. Plus, it enables collaboration. In GitHub, people raise issues. Like, this is the easiest way to get started with open source software, honestly. Just see the issues section of any repository, like on GitHub, any open source project. Over there, people will have raised issues like this is not working, that is not working. And then you can offer to either solve one of those issues, or if you see that something is not working or there's some typo, even then it's considered a good practice to raise an issue and then offer a fix. So this is done through pull requests. I think Rishabhaya already gave a brief primer on how Git and GitHub works, but that's not like really relevant to this discussion. But yeah, you have to be familiar with how pull requests and code merges happen, and how people can offer you feedback and how that works. So there are different version control system, as I said. Uh, GitHub is now owned by Microsoft. GitLab is, I think, run separately. Many organizations maintain mirrors on both sides. So have your pick, but don't like let it choose what kind of software you work on. Just because you're not familiar with GitLab and something is hosted on GitLab, don't like abandon it or whatever. Both of them are pretty similar. They're not that different. So that's about version control systems. So now we come to some important stuff in tooling and documentation, right? So I mentioned some tools like specific to Linux before. Now, how you document your projects? Like, technically, yeah, some people still upload PDFs, and you're just expected to read that PDF and understand shit from there. But usually stuff isn't documented like that anymore. So documentation tools are very, very essential, and communication is again very, very essential in an open source project, because one is, all open source projects have a very wide scope. Like, even suppose within my organization in Arduino, the guys who work in front end work entirely on a Java based IDE. the guys at the back end deal with C++ development. In the middle, you have some weird AVR stuff. Somewhere else, you have stuff that deals with assembly and hexadecimal level stuff. So at some basic level, the even the biggest maintainer, oldest maintainers of the project, they have only a very vague idea of what the whole software, all the parts of the software do. So you have to be very communicative, and you need to really talk and document your work properly. So there are a few things that most people use. Like one is Markdown. So Markdown is like if you've seen a README file with the MD extension, it's a Markdown file. So Markdown is like simplified HTML where you can use to annotate your files. So if you want to know why Markdown is used instead of just writing in MS Word or in Google Docs, one is because obviously it's not free software. So that's the thing. I mean, MS Word is not free software. And the second thing is with Markdown and other tools, all the other tools, you don't have to worry about stuff like font size and line spacing and paragraph spacing and all that crap. It's all taken care of. So yeah, Markdown, which is HTML style markup. If you've gone through repos which use Python a lot, you'll see restructured text. Okay, and uh, uh, these these README files usually have an RST extension. So why restructured text is good is, one is it's built into Python. So people who are like using Python will prefer using Python style syntax even for their docs. It's more internally consistent. And the second thing is you can take advantage of restructured text to build whole websites with documentation like RTD, which is read the docs. Okay, so uh, RTD can be used to like you can use restructured text. You can put all of your restructured text files in a specific order, in a specific way, and it's gonna build your tool for it. Like it's going to build a complete website. Like let me show you an example of an RTD project, which is MicroPython's documentation. Okay. So I'll just switch over the view to that page. So now you can see the MicroPython site, right? So this is a whole site which has only references, library reference, and it's got reference to every single board that MicroPython supports, every single library that MicroPython supports. And the best thing is uh, uh, these projects, they're very closely linked to the source code. Like you can build this RST documentation in such a way that suppose there's some, you can see this yellow code in these boxes, right? So you can build it in such a way that when your source code in your repository changes, this code on the website will also change. So yeah, it's actually pretty cool. So you can try to build an RTD site sometime. Hosting the site is free as long as it's an open source project and it's not on private repos. So that's how Read the Docs works. Now, obviously, apart from RST, you can use other stuff. There's Sphinx, there's MKDocs. Arduino uses something called ASCII docs to build their source. So all of these are documentation tools that you can use for open source projects. Most probably any open source project you're taking part in will use only one of these tools. So don't be intimidated. And usually the format is really simple. And knowing documentation and communication well is very handy. Like that's what makes the difference between like leading to a lot of confusion and a lot of clarity. And in case you have a doubt, it's better to over communicate rather than under communicate. Just remember this: it's fine if you're clarifying absolutely stupid shit to your project maintainer that, okay, I am going to make this button which is green, and when I click it, it's going to do this. And then when you click back, it's going to do this. It's fine if it's too explicit. But if you withhold information and you spend time building something and later that change doesn't get accepted, then you just screwed yourself over for no reason. So in such a situation, it's better to have good documentation and good communication skills. That's something that's very important. Now we come to something called CI/CD. Have any of you heard what CI/CD is? Anyone who's worked on DevOps and knows what CI/CD is? Anyone willing to explain stuff? Hello, is anyone there? Yeah. Hello. Yeah. Okay. So I'll explain what it is. So CI/CD stands for continuous continuous integration and continuous development. Okay. So this is exactly what it sounds like. Now, like, yeah, there's a lot of new words on the screen, but yeah, you can take a snapshot of that and later go search all this stuff up. It'll start connecting in your head. So basically, continuous integration and continuous development is like it's a different model from what we normally see. Like Windows, what happens? You have a Windows 7 release, and then you might have a service pack or some small security update, but no major change happens till like Windows 8 comes out, right? And between like Windows 8 and Windows 10, again, there's no major change. Now, open source projects can't really be developed like that. One is because it's risky, because a lot of people are working on the project, and say you start working on a project which is going to take 2 years to finish. You assemble a team of 30 people, but by the time 6 months are over, half of your team has left, and all of the code that you developed got abandoned. So for this, you need to adopt a CI/CD approach. Like you need to continuously build stuff and continuously push stuff. Okay. So what this means is you're going to make very, very small changes and add them frequently. Now, any open source competition or open source organization will tell you that they like something called atomic commits, like small commits. Whatever uh, commit you're doing, like whatever pull request you're sending or whatever code you're editing, that code should only do one thing. Like it should only do one thing, as in if you have two different changes to make, you have a file and like you want to change the background color from red to blue, and you want to change the spelling of one word. The changing of red to blue should be a separate commit, and the changing of the text should be a separate commit. The reason for this is, if you keep your commits small, then every time it can be errors can be traced back to a specific commit. Like suppose I change 5 features together and send one pull request, and that gets merged, and later on I discover that that's giving me errors in the software. So now I don't know from which of the five commits the problem came from, right? Like it could have been any of the changes you made. So that's why atomic commits are preferred. It's preferred that you commit often and you make small changes, like instead of making very big changes suddenly. Okay. So now, as you might expect, this CI/CD process comes with some baggage. Like some things which you only had to do once before, you have to do 10 times now. Okay. So, like, obviously, there are a few development practices that every software follows. One is like your tests. When you write any software, you have to build test cases for it, right? You have to test it on something, you have to use some dummy code. So now what happens is every time you write, like normally if you are following a CI/CD pipeline, every time you test, you'd have to do that. Then there's your build problems. Okay, like you have to recompile the software. Like every time you build a tool which needs to link multiple files together to execute, you have to again build the whole thing. Then you have to run it through unit tests, and then you have to install it, blah blah blah. So what CI/CD tools? There are some certain CI/CD tools that make this job easier for you. One example of this is say Travis CI. So Travis CI is a tool that comes integrated into GitHub. Okay. So what you can do in Travis CI is you can define a Travis .yml file, and what this file does is over here you can write which compiler you have to use, some basic tests that you have to run, and every time you push code, all these all this will happen automatically. Like what Travis will do is it's going to take your code, upload it to a server somewhere, run the tests on the server, and then tell you whether your code is passing those tests or not. So this is actually very useful from a maintainer point of view also. Suppose I want some new volunteers for my project, but I don't want them to break my project. But the thing is, sometimes those volunteers might submit absolute shit, like code that doesn't mean anything, or can't do anything. So if I have a good CI/CD pipeline, as soon as that guy sends me his pull request, his code is going to fail some of my requirements. Like either it's not going to fit in well with the rest of my code, or some test will fail, or the build will not complete. And that way, I can straight away reject his pull request even without looking at it, because they haven't like done enough due diligence to make sure that it works, or they haven't tested it enough from uh, their side. So that's what this thing is. So just like Travis CI, you have other tools like Jenkins. So this is also a free tool that does the same thing. So you have to get into that CI/CD. It's like a mindset more than anything else. Obviously, it's also a DevOps practice, but it's a way of working. You have to continuously build. In a way, even Git is a CI/CD tool. What you do is, instead of continue like building a software all together at once, you make small changes, push, small change, push. So and like that. So even Git is an example of a CI/CD tool. All right. So just this is known as pipelining or a workflow. Like your workflow is the series of steps that you follow, and this is very important, because in software development, like whether it's a hackathon style software development or a personal project, usually you don't have to worry about iteration. You create one version of a software and somehow that's enough, right? You don't have to worry about it after that. But when you're actually creating a maintainer, like a piece of software that needs maintenance, then you start running into these problems. Like I'll give you an example. Like for the code that I wrote, we'll switch over to that view again. For the code that I wrote for GSOC, it's C++ code only, so I think you guys will understand it. Even if you don't understand it, I think it's fine, because as long as you understand what I'm trying to do there, it should be enough. So this code is like, oh, this one file is over 1,000 lines. Okay, so now uh, I hope you all can like zoom in and actually see some of the code. So the thing is, I have to do a few things in this code. I have to find a particular keyword in a input file, then read if that keyword is the correct kind of keyword, and then I have to substitute the keyword for another keyword. That's how you translate one language into another language. Now there are multiple, like normally if we were writing a program, what we would do is I'd probably implement all of the logic at once. Like if I'm going to write about if statements, then I'm going to translate everything at once. I'm going to recover the if statement. I'm going to edit the if statement. I'm going to check if the if statement is what I want, and I'm going to, then after that, I'm going to edit everything. But that approach breaks down when you have a lot of like keywords, like this big class you can see here. These are all the keywords that are included. So what I did was I split it into three different parts. These matcher expressions that you can see here, the only job of these expressions is to merely find the keyword, nothing else. Okay, so these expressions, all they do is match. So I wrote the matcher expressions in one area. Then I wrote a class which has handlers. The only job of this code is to take that expression and send it somewhere else. It doesn't care what the expression is, if it's correct or wrong. And then finally, I wrote individual classes for every single case. Now over here, all it's doing is it's taking the input from that handler and then editing the keyword. So now you'll notice a few things. Now what I can do is I can edit the matcher without affecting the rest of the code. And since everything is in a separate class, if one keyword breaks, then the rest of the code will not break. So, you need to worry about things like that, things like modularization, or how modular your code is, like how many pieces is it divided into. Normally, it's always better to have your code as a series of interactive modules which have interfaces and which interact with each other, instead of one monolithic thing where your front end merges into your back end, and if your back end breaks, then your front end breaks, and vice versa. So try to keep things separate. Another good practice that most open source organizations follow is called TDD. I don't know if you've ever heard of TDD, but it's called test driven development. So this is exactly what it sounds like, right? So the problem with most people is they write the software, but they don't bother to write the test cases. They're like, okay, the software is already there, and why should we care about writing test cases? Like, we'll just like write something for the sake of it. In TDD, you do the reverse. You want your software to do something right, first write the test case. So first your step is you write the test case, then you develop for it, and then you develop until that software passes that test case, and then you deploy it. So this is an inverted way of working. Like, first you need to think, all right, fine, this is what I'm going to develop. But first, what kind of tests can I run? First, you need to develop those tests. Then when you run those tests, your software will fail those tests. And then you deploy your software. So the advantage of this approach is at each step of the way, you're going to make sure that your software is passing those new test cases as well as all the previous test cases. So this is what is known as test-driven development or test-driven deployment, or TDD for short. So this is something that you should get used to also, and this is a good way. This is a good development practice to keep in mind. All right. So finally, we come to the like last few parts, which is your code review and integration. Uh, like if you're working for a big organization, like say Debian or Debian or Fedora, for example, these have typically a multiple roles. I actually agree with what Akshat says. It is open source, but it's very hierarchical. You have a set of maintainers, then you have a set of developers. So what happens is GitHub defines different roles for different people. Like suppose as a newbie, you might not even be allowed to like you might only be allowed to make pull requests or read the code. You might not be allowed to do anything else. So that's the base level. And once you have been contributing to an open source organization for some time, you might get maintainer access. So this part is like, like now you have access to actually review somebody else's code with a group of people. And finally, you get full developer access where you have unlimited permission to push code to the master branch. Like typically code is developed in branches, right? You don't want every small incremental update you do to be reflected in the main version of the software, especially if you're developing something very critical. You want to maintain separate branches of your software, like a version alpha or a version beta, and the version that's ready for like that people are supposed to be installed can be live in the master branch. So the people at the top of the chain are usually the people who can commit directly to that master branch. All right. So those are a few of the things to keep in mind. So, just like I know this is a lot to take in, but these are the things you have to keep in mind while working for open source. And ultimately, you have to realize that it is like obviously there is money involved in open source projects. That's why some of the biggest open source projects today are actually held by private companies. I believe the biggest contributor to GitHub are actually companies like IBM and Google and Microsoft, and not like individual people or groups of people. So obviously that is there, but more than that, it's an ideological thing, and it should line up with what you believe in. You might not be okay with the way certain code is handled or the way projects are managed or something, then don't work on it. You need to uh, define your define your stuff. Then again, there's some more stuff like, yeah, how you commit, proving your identity. Okay, so I think I'd say this comes under tooling as well. You have PGP keys, like GPG encryption. So this Rishabhaya recently asked a poll about this. So what happens is in open source software, obviously your identity is extremely important. People trust a person, a particular person. Now it might be that for some reasons, or for even obvious reasons, suppose you're working at some company, you might not use your original name like on GitHub, or you might uh, use multiple accounts, or there is some other reason, but it should be extremely clear to verify your identity. And this is where PGP keys come into play. A PGP key is like a 2048-bit long key that you can use that key to sign your GitHub commits. Like your key is something that only you know, and you have it stored somewhere very safe, like in an encrypted key, in an encrypted key wallet or on some offline media or something, and you use that key to sign your commits on GitHub. So more than your name or more than your this thing, they can verify by that key that you are the person you are claiming to be. And how are these keys typically granted? Is that there's often a key, a key verification party where people actually come online in meetings, or they actually even meet up in person. For Linux based projects, there are Linux user groups that you can join, and you have to key signing party, and over there you can meet the maintainers of the project, and they'll actually sign your key, verifying that you are who you claim to be. And later you use that key and verify your identity with that key. Obviously obviously it's very important that you never lose that key also. So, and again coming back to code review and integration. So that's how you communicate. You go back and forth. Sometimes you might just be given suggestions that you need to do A, you need to do B. Sometimes the if the suggestions are extremely small, usually the maintainers of the project themselves make the edits, and they tell that okay, I made the following edit. If you accept it, then we can merge the two requests, and then you can send a pull request, and then it will later get merged. All right. So that's also possible. So in conclusion, finally, what does open source software offer? It offers to work on real large scale software. So like a project, however big a personal project be, I mean, unless it becomes a startup or a company in its own right, it's still a demo, right? I mean, other people are not using it and all that. But once you get into open source territory, you're building stuff that thousands or if not millions of people use. And these code bases are as complicated or even more complicated than the code bases used by companies. Like the Linux kernel has millions and millions of lines of code in it. Clang itself has over a million lines of code in it. So this gives you an experience of how real world software development works and how real world software looks like. If you do some open source development and you like the experience, the least you can say about yourself is that your life as a software engineer is not going to suck. Like, at least you know that, okay, fine, I can tolerate my job, at least the main core of the job. So, that's one way. You'll actually be working on what you're going to be doing in the future. It's not a proxy or anything, it's the actual thing. So you can work on real large scale software. You can build connections with people. So again, most of the people working on open source organizations or projects, they are usually people working in top tech companies, or they're professors, or even suppose in GSOC there were professors from UW, DRAC, ETH, Zurich, CERN, and all that had hosted projects. So these people are like influential. They know other people. They know communities. They can get you introduced to other people, and you get to form real connections with these people. You get to meet cool people. You get to network, and that is very, very valuable. I don't think I need to tell you how valuable that is. So that's the second thing. And finally, yeah, it's cool. Like that's what I'll uh, conclude my talk by saying that it's very cool, man. You get to build stuff that others use. You get what you build is used by thousands and millions of people. And as a software engineer, I don't think there's any greater satisfaction than that. So for that, I'll conclude the first part of this thing, which was the talk on open source software. We'll talk about the point blank groups for a bit before breaking up, like for this meeting. If anyone has any questions, then please ask me right now. Anyone has any doubts? Any doubts? Any questions? Any comments?
भैया
Yeah,
भैया बोल रहे हैं दैट जैसे कि आप कोई रेपो देखते हो कोई प्रोजेक्ट देखते हो राइट आपको
yeah,
मीन्स उसका वर्क उसका कोड समझ में आता है आपको उसमें कुछ बग मिलता है फाइनली ठीक है
yeah,
तो
yeah.
मीन्स कैसे एश्योर करेंगे दैट जो आप पुल रिक्वेस्ट क्रिएट कर रहे हो वो
Hello? Yeah? Hello? प्रतीक आवाज कट रही है.
आई थिंक नेट का इशू होगा.
हाँ. Anyway, I'll stop sharing for now because I want to, I mean, not stop sharing, I'll stop recording that we can upload up to this extent somewhere. I